we chase one of those questions that sounds like science fiction, but is very real. Could Einstein be wrong about the speed of light? Scientists just pushed that question further than ever before, using the universe itself as a laboratory, tracking the fastest, highest energy light from the farthest reaches of space to see whether photons of different energies keep perfect step across cosmic distances. What they found, and what they didn't find, tells a story about the limits of current physics, the stubborn durability of relativity, and the narrow hiding places where new physics might still lurk. Strap in. We're following light on the longest journey imaginable. Chasing light across the cosmos. Imagine flicking a flashlight from one shore of the ocean and watching it arrive, perfectly timed, at the opposite beach. Now imagine doing that across the universe. Light that left a distant galaxy when Earth's continents were arranged differently, photons that have sailed for millions or billions of years to reach us. If Einstein's postulate is right, every photon, no matter its color, energy, or origin, travels at exactly the same speed in vacuum. But some cutting-edge theories that try to reconcile quantum mechanics and gravity hint at the tiniest of differences. A higher energy photon might arrive a hair earlier or later than a lower energy cousin. Tiny timing differences stretched across cosmological distances could signal a new layer of physics, or else tighten the rope around where new physics can hide. A new study led by researchers at the Universitat Autönoma de Barcelona has just subjected Einstein's speed of light rule to one of its most severe tests yet. By combining measurements of very high-energy gamma rays from distant cosmic sources with a novel statistical technique, the team probed whether photons of different energies travel at different speeds. The verdict? No detectable difference. But the null result is far from empty. It tightens existing limits by roughly an order of magnitude, dramatically constraining many quantum gravity models that predict Lorentz invariance violation. In short, Einstein passed the exam again, but the test also shows us more precisely where to look next. Why question a principle that works so well? Lorentz invariance, the idea that the laws of physics, including the speed of light in vacuum, are the same for all observers, is woven into both special relativity and the standard model of particle physics. It has survived a century of experiments, so why poke it? Because two of our most successful frameworks, quantum mechanics, which governs the small, and general relativity, which governs gravity and the large, do not mesh neatly. Many candidate theories of quantum gravity predict that Lorentz symmetry might fail at extremely small scales or at extremely high energies, producing minute energy-dependent deviations in photon speeds. Those deviations would be minuscule, far beyond the reach of tabletop labs, but amplified over cosmic distances, they could leave detectable timing fingerprints. Testing Lorentz invariance at the highest possible energies is therefore one of the best ways to catch a glimpse of physics beyond our current theories. The cosmic timekeepers, very high energy gamma rays. To test whether photons of different energies arrive at different times, you need two ingredients: extreme photon energies and vast travel distances. Enter very high energy gamma rays emitted by the universe's most violent accelerators, blazars, pulsars, and gamma ray bursts, sources that fling particles and photons to energies millions of times higher than visible light. These gamma rays travel billions of light years before reaching Earth, and any tiny speed variation would accumulate into a measurable delay between high and low energy arrivals. But measuring those arrivals is not trivial. High-energy photons are scarce and require specialized ground-based observatories, Cherenkov telescopes and other detectors, to spot the fleeting showers they create in Earth's upper atmosphere. The UAB-led team didn't rely on a single source, but combined a wide set of measurements from multiple observatories and events, applying a clever statistical framework to squeeze the maximum information from the data. That breadth and method is what lets them push limits tighter than before. A new statistical technique combining the cosmic clues. One of the major advances in this study was methodological. Rather than analyze single bursts or isolated events, the researchers developed a new statistical technique to combine multiple high-energy measurements, each with its own uncertainties, into a global constraint on Lorentz-violating parameters described within the Standard Model Extension (SME) framework. The SME parameterizes possible symmetry violations, letting theorists and experimentalists speak the same language about where Lorentz invariance might break. By aggregating data, the team amplified their sensitivity to minuscule effects that would otherwise be lost in the noise of any single observation. The result? Stronger bounds and the shrinking of theoretical parameter space where new physics could hide. What the results actually say. The headline is simple. No evidence was found for energy-dependent speed differences in the photon data analyzed. That null detection tightened the constraints on some SME parameters by about an order of magnitude compared to previous studies. Practically speaking, many toy models that predict Lorentz symmetry breaking at accessible energies are now far less tenable. But the null result is not the death of novel physics. It is a map, showing where the anomalies are not, and pointing us to the more elusive territory where a breakthrough might still occur. The team is careful to emphasize that absence of evidence is not proof of absence across all models. The constraints depend on the specific SME parameters tested, on assumptions about the astrophysical emission times of different energy photons, and on the energies and distances probed. Still, improving limits by an order of magnitude is a major step. It rules out swathes of parameter space, guides future instrument design, and focuses theoretical attention where it should go next. Why next-gen telescopes matter, Cherenkov and beyond. If this test tightened the rope around many versions of new physics, future instruments will still be essential. The Cherenkov Telescope Array, CTA, and other next-generation observatories will detect gamma rays with far greater sensitivity and energy reach, enabling tests with better statistics and over broader energy ranges. CTA, with its global array of telescopes, will increase the number of detectable very high-energy events and improve timing resolution, letting scientists either push limits even further or, if nature allows, finally catch a deviation. The new UAB-led paper shows the power of combining data now. CTA will supply the raw data to push the method to even rarer regimes. The next era, telescopes that test reality. The upcoming Cherenkov Telescope Array, CTA, will transform this field. With far greater sensitivity, higher energy reach, better timing precision, a global network of observatories, CTA will dramatically increase the number of usable gamma-ray events. That means more distant sources, shorter bursts, sharper temporal resolution, tighter constraints. If Lorentz symmetry is ever going to crack at observable energies, CTA is one of the instruments most likely to see it. And if it doesn't, then relativity will stand stronger than ever, not as a dogma, but as the most thoroughly stress-tested idea in physics. The real victory of this discovery. The true triumph here is not that relativity survived, it's that we can now test it using the death throes of stars, the jets of supermassive black holes, the faintest echoes of ancient explosions. We are no longer limited to Earth. We use the cosmos as our laboratory. Every distant flare becomes an experiment. Every photon becomes a probe. Every null result becomes a sharpened map of the unknown. We are learning not just what is true, but where truth still has room to surprise us. If you want to explore the edges of reality, where physics meets mystery, where the universe itself becomes the experiment, subscribe to Discovering the Unknown. Because the unknown isn't waiting in fiction, it's arriving, one photon at a time, from the farthest reaches of space,